Okay, well, welcome back. Let's see, we were talking about evolution, and we've just gotten done talking about Darwin and his ideas. But let's face it, it's been like 150 years since Darwin was first publishing his work, and our understanding of evolution has definitely matured since he wrote what he wrote. So, for example, he didn't know much about genetics. I mean, he knew nothing about genetics to speak of. He was like, I think he was one of those people who thought about that spermist hypothesis, if you remember from chapter 6. Anyway, or blending or something along those lines. So, just a quick review here of what we learned from him. Evolution is genetic change over time. What we know now is that we can easily measure evolution by looking at change in allele frequencies, very, very specific change in allele frequencies. And so we've been dealing with alleles for a couple of chapters now, and they don't go away. So think about a population of tigers. Here's our pie chart. And the orange part of the pie chart is the proportion of orange fur pigment alleles. Again, I'm not saying the proportion of orange tigers, we're saying it's the proportion of orange alleles in that tiger population. And then we have the proportion of white alleles. And it does turn out that orange is dominant and white is recessive. If over time we start to see this change in the pie chart, where the orange is becoming more and more rare, still not completely rare, but it's becoming less and less abundant, and the white allele is becoming more and more frequent or more and more abundant, what you have is evolution. That is literally evolution. And so that's really important to embrace, that you really understand that anytime you're going to see a change in that pie chart, that's evolution. So the other thing that's important to know is that individuals are not the ones that are evolving. In other words, Lamarck was wrong. It's not the individual that changes, it's the population that changes. So we can talk about individuals and how they are carrying, alleles, right? But an easier way to think about this is just kind of dissociate the individuals from their alleles. So we don't want to think about the individual frogs in this population. We want to think about how many green alleles there are in the population, how many purple alleles there are in the population, or how many red alleles there are in the population. So we call this the gene pool. We're literally saying the individuals, they matter because they're carrying these alleles. But when it comes to evolution, the individuals don't matter as much as just the change in the gene pool. So again, this is just kind of an example for you, and I guess it would have been better to have 2 green dots for every green frog, but the picture just shows one. So we talk about allele frequencies and allele frequencies changing, and this gets us into some math. So a trait does not just decrease or increase in frequency because it's recessive or because it's dominant, right? The recessive alleles don't simply decrease because they're recessive. And dominant alleles don't simply increase because they're dominant. Not how it works. So we have to get into the math of this to understand how it works. And some mathematical definitions for you. Our first one is the mathematical term p. This is a lowercase p. And lowercase p is defined as the frequency of the dominant allele. Frequency is a mathematical equation, which is simply how many of a subset divided by the total. So if p is the frequency of the dominant allele, the math that we have to do is figure out how many dominant alleles there are and divide it by the total number of alleles, and you will get the frequency of the dominant allele. Q is the opposite, and that's a lowercase q. It's the frequency of the recessive alleles. So if we only have 2 alleles in the population, then we can do p plus q equals 1. And the reason for that is if you're doing a number divided by a total, and this is the other version of it, they're going to add up to 1, right? Because adding those 2 together is going to be the total. Okay, so that's the definition of p and q. So if we were able to calculate p and q at P equals 0.2 and Q equals 0.8, then there's a couple of things that you can do with this. Like, for example, you could predict what the genotype frequency should be, assuming lots of things, and we'll get into those assumptions in a minute. So basically what you could do, one way you could do it is you could figure out the frequency of these genotypes, and all of these are calculations of genotypes, by simply squaring P. So 0.2 times 0.2, that could give you the kind of the predicted frequency of the homozygous dominance. Q squared, if we wanted to predict what the frequency of the homozygous recessives would be, then we would do 0.8 times 0.8. And if you wanted to figure out the frequency of heterozygotes, you do 2 times 0.2 times 0.8. And that would give you the frequency of the heterozygotes. So all of that's important, but it's also important to remember that we're talking about a frequency. And I've defined frequency for you as being a division. So if you know the number of homozygous dominants and you know the total number of individuals in the population, you don't have to square anything. You can just do a division, the number of homozygous dominants divided by the total. And you can do the same thing for Q squared. If you know the number of homozygous recessives, you can just divide by the total and you can get the frequency, and you don't have to square anything. Same thing here, 2PQ. You don't have to multiply those together. If you know the number of heterozygotes divided by the total, you can get the frequency. Just like with P and Q, since these represent all the possible genotypes in the population, we would be able to say P squared plus 2PQ plus Q squared equals 1. And that's of course because we're dividing by total. Okay, hopefully that makes sense to you. If not, you can refer to the lab on this. But we're going to move on to talk about how we can use this information to calculate all the information that we need to calculate. And your book does a pretty good job of stepping you through this. So that's what we're going to do. We're going to take a look at this parents generation here, and your book has some good math here. It's nice and round. 1,000 is the number of our kangaroo rats in this parent generation. Because it's a whole population, we're not calling this the parental generation. It's just the first generation. And what we're going to try to do is try to understand this Hardy-Weinberg equilibrium. Hardy and Weinberg were the two scientists who figured out this math of evolution. They're the ones who independently realized that if you look at the genotypes, you can figure out the allele frequencies. And they started out this whole proposition by saying, evolution doesn't always happen. And it's true, it doesn't. Oh, how can we figure out the math of a population that is not evolving? I mean, that's way easier to figure out, honestly. So once we can figure out how the math of how a population is not evolving, well, then we'll figure out what happens when a population is evolving. So here's the math. And again, that's called equilibrium, just so you know, equilibrium. So here's the map. We've got 3 genotypes. And the nice part about this example is that this trait of the heterozygote, right, you can actually just look at them and know they're heterozygous. This gets away from some of the difficulties that you might have. You know, we've got like a little codominance going on here where it's spotted, that you might have if the brown allele was completely dominant or normally dominant, because then the heterozygous would just look exactly like the homozygous dominant. But it's not. In this kangaroo rats, we've got these spotted codominant kind of thing. So in this population of 1,000 kangaroo rats, and if you don't believe me that there's 1,000, just add 16 plus 222 plus 762, and that'll get you to 1,000. In this population, there are 16 homozygous dominants. Again, doesn't quite work because they're the codominants, but whatever. Let's just go with this language. There's 222 heterozygotes, and there's 762 homozygous recessives. And you might be asking yourself, why are there so many homozygous recessives? Shouldn't it be the other way around? And the answer is absolutely not. Evolution doesn't just say that the big B allele will become more and more common. It has to do with which individuals are surviving to reproduce in the environment that they're in. And so in this particular environment, the light brown kangaroo rats were the ones that were doing better. But let's just say, for argument's sake, that evolution isn't happening right now. So how can we figure out P and Q? Well, it's actually not too hard. You can take the 16 kangaroo rats and you can understand that each of these 16 kangaroo rats has 2 big B alleles. And because they have 2 big B alleles, we can add those together and we can figure out that there's actually a total of 32 big B alleles in these 16 individuals. If you look at the heterozygotes, you can see that there's 222 heterozygotes, but each of them only has 1 big B allele. So what we end up doing is we add 16 plus 16, or 32, plus 222. So 16 times 2, that's each of the big B individuals have 2 copies. And the 222 is the number of heterozygotes because they each have 1. Guys, I'm going to take a second here and tell you that a common mistake people have when they are going through this math is that they say, well, this one has 2, but this one has half as many. You can't do that. You're not going to cut 222 in half. You're saying there's 2 big B's, so 16 times 2, and there's 1 big B, so 222 times 1. Don't cut this number in half, whatever you do. Okay, so we've got 1,000 kangaroo rats. We know that it's 2 times 16 plus 222, which equals 254 if you're following along with me. And that's the subset. We have to divide it by a total. And I told you that there are 1,000 kangaroo rats in the population. But because each individual has 2 alleles for that coat color, there's actually 2,000 alleles. So we got 254 divided by 2,000, and that gives us 0.127. If you don't believe me, do it on your calculator. You can do the same thing for Q. We can look at these 762 individuals, and we can say, oh, well, each of those 762 individuals, they've got 2 little b alleles. And so if you multiply 2 times 762, you get 1,524. But of course, there are some little b's in these heterozygotes. And so we just need to take those 222 and add it to it. So 1,524, which is 2 times 762, plus 222 is equal to 1,746. Again, if you don't believe me, do the math yourself. I do encourage you to do the math yourself. We're still dividing it by the total number of alleles, right? We're just kind of looking at the subset of little b's now, but this total number of alleles has not changed. It's still 2,000. And so we get the number for Q, or the frequency of the homozygous recessive, to be 0.873. Okay, so I know that was a lot of math. Again, there's a lab that goes over this, so hopefully you're embracing what that lab has to teach. But let's see what happens with equilibrium in the next generation. Now we got to make some assumptions. I'll talk more about those assumptions later, but for now we're going to assume random mating. So of these 1,000 individuals, just assume that you got a random chance of mating with the next kangaroo rat that's near you, and you're going to make babies with that one. And some of you make eggs and some of you make sperm. And so, right, half of the population is making eggs and half the population is making sperm. But the ratio is still going to be the same. The frequency is still going to be the same. So we can figure out what the next generation is going to look like simply by multiplying not big B times big B, but P times P. And that will give you the predicted genotype frequency in the next generation. Assuming, again, a lot of assumptions here, assuming that there will be no evolution. There's nothing that says that the big B is favored or the little b is favored. Now there's 2 ways to get a heterozygote. You could be a heterozygote if this egg meets up with this sperm, but you could also be a heterozygote if this sperm meets up with this egg. And so that's where the idea of 2pq comes from. There's two different ways to be heterozygous. And then of course, q times q that's q squared, and you're going to get 0.762. So if you multiply those numbers times 1,000, you will actually get the original numbers of 16 big B's. This is a prediction, remember. And 222 big B little b's, and 762 little b's. Again, we multiply 1,000 times 1,000 because we want to kind of be able to compare the original population with the new predicted population. So we want kind of the same numbers. So that's what you come to. The next generation, if there is equilibrium, if there's no change, and if you have random mating and no evolution, the frequencies of the alleles will be the same. And we predict that the frequencies of the genotype should be the same too. No change over time. However, the assumptions that I keep talking about, those are hard assumptions to meet. I mean, for equilibrium to happen, for no evolution to happen, we need to meet these 5 assumptions. The first one is that there's no natural selection. Like, everybody who's born survives, or if they do die, they're dying in equal proportions. It doesn't matter what their coat color is or all those other things. There's no natural selection. We also have to assume that there's no mutation, right? Because the thing about mutations is that they bring in new alleles. So they can't have any mutation happening. You can't have any migration. Now, I don't like this word migration. It's the one that your book uses. I prefer the word gene flow. So from now on, when we talk about migration, I'll be using the term gene flow. That is in your study guide. There should be no genetic drift. And genetic drift just means random changes in population alleles due to completely random stuff. Has nothing to do with natural selection. And then, of course, you have to have that random mating thing. If any one of these assumptions is violated, then equilibrium will not happen. That means you will not get the same allele frequency in the next generation, and evolution will occur. So that's why this math is so useful. All right. Again, lots of chances to work with that math in lab, so I'm not going to go into it during lecture. Instead, I want to just really quickly make sure you have in your notes the idea of how to calculate the Hardy-Weinberg equilibrium if you only know phenotypes. So I'm just going to do this really quickly with you. And we're supposing that instead of being given an allele frequency, like P and Q, let's say you only know the phenotypes. And we're also going to say that we can't see the heterozygotes just by looking at them like we could with the kangaroo rats. Instead, you know, the dominant is showing in the heterozygote and the dominant phenotype is showing in the homozygous dominant. So you can't tell the difference between them just by looking at them. So we're not going to be able to do this because I'm doing it online, but you can kind of think about this, how many people in the class have attached earlobes versus how many individuals in the class might have unattached earlobes. And if you remember, attached earlobes is the recessive trait, and unattached earlobes is the dominant trait. If you have unattached earlobes, those little dangly earlobes that most people do have, dominant does not mean most common, but in this case it is related. So you could step through this, and I'm just going to make up some numbers for you. Maybe you could write them down so that when I'm going through this, it's going to make sense to you. Okay, so let's assume that in the class there's 25 people. So that's our total. And of those 25 people, we're going to say that 15 of them have attached earlobes. Now that's the recessive. So we can give them the genotype of little a. And that means that 10 of them are going to have unattached earlobes. Now that's the dominant. So their genotype could be big A, little a, or it could be big A, big A. We're not sure. And because we're not sure, The only thing that we really know is that 15 out of the 25 are little a, or homozygous recessive. And if you do that math, 15 divided by 25, 15 out of 25, you get the answer of 0.6. This is the frequency of the homozygous recessive, which of course, if you remember from before, the frequency of the homozygous recessive is defined as Q squared, which is our first bullet point right here. So the number of attached earlobe people divided by the total number of people in the class, 15 out of 25, gives you the frequency of the homozygous recessive. Now, at this point, we've gotten all that we absolutely know. 0.6 equals Q squared. But now we can start going through this idea of kind of estimating or predicting what we think Q would be. Now, we're not going to be 100% sure. We do know that Q squared is Q times Q. So if we take the square root of Q squared, we're going to get Q. If you take the square root of 0.6, you get 0.77. 0.77 is going to be Q. Take a second and do this on your calculators. Play along at home. If I have Q though, and you can pause this at any time as I'm going through the math with you, you're going to get the estimated frequency of the recessive allele. Again, we definitely know the frequency of the homozygous recessive. We've estimated the frequency of the recessive allele. But if we know Q, the estimated frequency of the recessive allele, we know P, because we know that P plus Q equals 1. So if Q equals 0.7, then what we could do is we could just take 1 minus 0.77, and that gives us the number that we need to have, which is 0.23. And this is a little bit of rounding, so if you're playing along at home on your calculators, I have rounded. But basically what I need you to know is that P is equal to 0.23. Once we know that, once we know that P is equal to 0.23, all we have to do to get P squared is to multiply 0.23 times 0.23. And if you do that, you get this pretty small number for P squared, which is 0.053. Again, a little rounding there, so if your number isn't exactly what I came up with, that's okay. The last number that we have to figure out is 2PQ. That's the frequency of the heterozygotes. And you're going to take the number 2, and you're going to multiply it times P, which is 0.23. And you're going to multiply that times Q, which was 0.77. So as I'm doing this, as I'm talking to you, we're just going to do 2 times 0.23 times 0.77. And from that, I get the frequency of the heterozygotes is equal to 0.35. That's what 2PQ is equal to. If you want a calculator online, you can always go to this calculator right here. It's a nice one. It's available online. And you can do all the calculations in another window from that web address. Okay. So I know there's a lot of math, and we're going to get lots of experience in lab. So, hopefully you'll start to understand what I'm talking about. The basics for this is that if P and Q change, then you get evolution. And if P and Q remain the same, then you don't have evolution. That's the whole reason that we went through all that math. All right, so if P and Q change, you have evolution, and there's 4 mechanisms of evolution. And you're probably already familiar with these. Like, we've already talked about natural selection, and we'll talk about it more as time goes by. Your book uses the word migration here. Remember, I use the word gene flow, and I want you to know the word gene flow. Migration is such a challenging word because it means it has too many different meanings. So we're not going to go with the idea of birds migrating and dirt. That's not what I mean. I mean like a permanent move from one population to another. That's what we mean by migration or gene flow, more importantly. There's genetic drift. This is a random chance changing the allele frequencies. It's not related to reproductive success. And then you have mutation, and all that mutation does is it gives you a new allele, new variation. And without variation, you can't have evolution by any form. Okay, so these are the 4 mechanisms of evolutionary change. And also notice that they're the exact opposite of the Hardy-Weinberg equilibrium assumptions. Remember, those were no mutation, no genetic drift, no migration, no natural selection, and the last one was you have to have random weeding. But we're not going to talk about that one. We're just going to stick to our 4 mechanisms here. So mutation, we've talked about mutation for several chapters. It's just an alteration of the base pair sequence of an individual's DNA, and when you alter this code, this genetic code, you get a new sequence of DNA, and that new sequence of DNA might actually change the allele. It might often end in a different protein. So if you end up with a different protein, you might end up with a different phenotype, and well, that could be bad, but it doesn't have to be bad. It could be perfectly fine, or it could be beneficial. Not all mutations are bad, but a lot of them do tend to be bad. When mutation happens, when a new allele is introduced, you are changing the allele frequency. By definition, you have a change in allele frequency. So you've got evolution. So what are the causes of mutation? We talked about this, and you probably read about this a little bit, and I talked about it in one of my previous lectures. Basically, you got a couple things. You can either have bad mitosis or meiosis, right? Where when you replicate the DNA, you're not replicating it properly. Or you could have some, that's by chance, right? By going through cell division. Or you could be exposed to some chemical or some physical mutagen, something that causes mutations. So some common mutagens are ultraviolet light, tanning beds, not a good idea. They cause skin cancer, they cause mutations in the DNA of the skin. And of course, smoking is a chemical danger that can cause cancer, and it's just a Far Side cartoon. The real reason dinosaurs became extinct is they were, smoking behind the cave there. I don't know, it just makes me laugh. So there you go, you get to laugh too, if you like. So the thing to kind of keep in mind about mutations is that not all inherited mutations increase in the population just because they've introduced the variation. You can have increase as long as the mutation is not damaging. If it's damaging, then the allele is probably not going to last in the population, and so it's not going to lead to evolution. That's just kind of something to keep in mind. Our next type of cause of evolution is genetic drift. And genetic drift is random change in allele frequencies due to chance and chance alone and for no other reason. Your book gives the example of dimples in your chin. Having a dimpled chin does not help you survive better. I mean, I'm trying to imagine how having a dimpled chin is going to help you survive better. Maybe it could help you reproduce better, but I don't know. Some people like dimpled chins. And so, but what we're talking about here is chance. So what we do is we're just going to roll the dice. And if you have a dimpled chin and it comes up with an even number, then you die. And if it comes up with an odd number, then the smooth chin people die, right? This is completely chance. But due to chance events, you can randomly be rolling more even numbers than odd numbers, or vice versa. And you can get the population kind of changing with the proportion of dimpled to non-dimpled, changing over time. And remember, that's evolution. So evolution can happen due to chance. It's possible for evolution, just by chance and chance alone, to end up going to something that we call fixation. And this pie chart here shows fixation, where basically you only have one allele in the population. So in this case, it would be like if dimpled chins didn't even exist, because it's fixed. That's actually the right way to say it. It's fixed for smooth chin in this case. Okay, so the key thing to take away from this is that random chance can change allele frequencies, and if random chance, called genetic drift, if that random chance changes allele frequencies, then you got evolution. So the thing about genetic drift, and it gets a little complicated, but the thing about genetic drift is that it tends to happen in small populations. Like if you think about it, if you got a small population, then this random chance event accidentally killing off all the Dimpin' people, I mean, that's not gonna happen like if it was a big population. So these random chance events happening in a small population are much more likely. Think about it this way. If you have a penny and you flip it 10 times, you know, your chances of getting 50-50 heads and tails are pretty good. You could flip it 10 times and get 10 heads. That's possible, right? It's not outside the realm of possibility. Like, that's a chance event. That's like a fixation chance event, only getting heads. Now, flip that same coin 1,000,000 times. What are your chances of only getting heads? Like, you can't even imagine what that would be like, because it's just not likely to happen. So because of that, that's why these small chance events in small populations are much more likely to end up in having fixation or to having changes in the allele frequency. Now, there are two special types of genetic drift. One is called the founder effect, and the other is called a population bottleneck. And I'm going to step you through each of those. The example that I'm going to give you for the founder effect is a little confusing, so be patient as I step you through the confusing thing that is the founder effect, especially the example that your book gives. I mean, it's a great example, but still a little confusing. So the example that your book gives is for 6 fingers, and this photograph that you see here is one way that you could get 6 fingers. You could have like an extra thumb. You could also have an extra pinky over here on this side. And these days, if you were born with 6 fingers, you know, they kind of just like chop that part off, and you might not even know that you had 6 fingers. Now, imagine that there's this population, and I'm saying imagine, but really this actually happened. Okay, so, and this happened actually in the group of people called the Amish. Now, the Amish were a group of people who lived in Germany, and they were persecuted for their religious beliefs. They didn't like change, and they didn't think that we should be embracing modern ideas, so they were keeping to the old ways. It just so happened, though, that one of the founding members of the Amish religion had 6 fingers. Like, this is a chance event. But the even more interesting chance event is that the Amish were isolationists, and they isolated themselves out of the whole population. For example, you should know that if you wanted to become an Amish person, you couldn't. The only way to be Amish is to be born into the Amish religion. And so the founding members of the Amish population happen to have a higher frequency. It's just a small subset. They happen to have a higher frequency of 6 fingers because the leader, who had lots of kids, of this small group had 6 fingers, and he passed his 6-finger trait on to his offspring. And so this small isolated population, this is the one that picked up and moved to the United States. Now, we would call this migration, but I'm not going to call this gene flow. And this is why those two different terms are so important. Migration, moving from one place to another, yes, that happened. But it's not gene flow, because for it to be gene flow, we really need to have the new population mingle with the population that's moving in. And that's not what happens with the Amish. They moved to the United States, but they kept to themselves. So what we can see is that they have a much higher proportion, the population of Amish have a much higher proportion of 6 fingers compared to the non-Amish population, like we see kind of here in this pie chart. Founder effect. Having a member of the founding community having a slightly higher proportion of allele frequencies is evolution. because it's a change in allele frequency from this population as a whole to this new smaller subset population as a whole. Again, a little bit of a confusing example, but it's a real world example, and so it's a good one. Founder effect differs from population bottlenecks because with population bottlenecks, instead of a population kind of leaving the home and starting a new population, what happens is that everybody else dies. And so the new population is a subset of the old population, but only because everybody else died. The key here is to understand that it's not because of natural selection that they died. It's due to random chance events, kind of like a forest fire or an exploding volcano or something along those lines. Random chance events leading to only a small subset surviving. And of course, that small subset that survives couldn't possibly represent exactly the same allele frequency of the original population. It's called a bottleneck effect because if you think about like little beads in a bottle, and you just happen to spill out a few, like a small handful of those beads, you're not going to get the same proportion of beads that spill out as there were originally in that bottle. So the bottleneck kind of says that you're getting just a small subset in your new population. Again, also the difference between bottleneck and founder effect is that with population bottleneck, everybody else dies, and with the founder effect, it's that a small non-representative sample leaves the old population and founds, I know that sounds weird, but that's how you say it, they found a new population. Okay, well hopefully that makes sense, but I'm going to pause this now because this is a good stopping place.